Good evening, everyone. So, yesterday we have completed Harmony. So, today we are going to start Oscillations. So, welcome to the class. I think JNV Mahe, JNV Bhandara, JNV Kolhapur, all are here. Okay. So, in this chapter, this is again an important chapter for the point of view of your CBSE exam as well as the JE exam. At least one question come from oscillation. So that's a good chapter to be studied. Okay, so we will start. First, confirm is everything clear, everything visible. My voice is audible. Just confirm it, and after that we will start the session. Okay. So first of all, we will see what we are going to uh, study in this session. Actually, first of all, there are actually this lecture is somewhat basic lecture, somewhat you will say that basic fundamentals will be discussed in this chapter. From the next lecture, we will discuss some numericals, some important derivations, some things like that. Today's session is going to be a basic lecture. Okay. There might be few things that you already know, so don't just panic. Be with the session. Okay, so let's start. First of all, the first thing is we will start the session with the simple definition what is periodic motion. The periodic motion, if I say any motion which repeats itself after a fixed time is called a periodic motion. Like if I say that Earth is revolving around the sun and it repeats its motion every 365 days or somewhat the similar time, it repeats its motion every year. You know that. If I talk about in your room where you are sitting, I think there must be a clock watch. क्या कहते हैं उसको? Wall clock, actually, I think that's the right word, or a wristwatch, you can say. Uh, there are minute hands, second hands, and the hour hand. Every hand of the clock repeats its motion. Like if I say the minute hand, if I say, let's suppose this is the minute hand, this is our clock, and this is our minute hand. This minute hand will repeat its motion. It will again reach at 12 after how many minutes? You will say 60 minutes. So minute hand will repeat its motion after 60 minutes. So I am just saying that there are a lot of examples. If you say your mess opens at 9 a.m., if I take a random number, your mess opens at 9 a.m. and every day you go there and take your breakfast. So this is again, you can say this is a repetitive motion. This is a periodic motion because after a certain time or fixed time, I am going to the mess from my dormitory to the mess. So this is again a periodic kind of motion, but not exactly periodic, but you can consider the things as periodic. So what is periodic motion? When a body repeats its motion after regular time interval. Regular time interval, you can say any fixed time interval. Then its motion is called as periodic motion. Like I have already given some examples to you. Still, you can see that motion of Earth around the sun is a periodic motion. The motion of clock hand. This can also be considered as a circular motion, or you can say uniform circular motion. Uniform circular motion is an example of periodic motion. So what is the highlight of the periodic motion? When the motion is repeated, first highlight. Second highlight is after a fixed time interval. Only then it is called as periodic motion. It's not like the motion is repeated and you will call it periodic motion. No. it has to be repeated after a fixed time interval, then you will call it periodic motion. I think two main points are highlighted there. Moving further, what is oscillatory motion? What is oscillatory motion? Listen to me very carefully. If I say there is a periodic motion, and if you add some boundaries in it, what you can add, if you add some boundaries in it, then the motion becomes oscillatory motion. What is the meaning of this boundary word? If I say, have a look at that, just consider the things I am saying. Suppose there is a hemispherical surface like that, and this surface is very much smooth. Clear? The surface is smooth, hemispherical surface, and you dropped a ball from here. From this point, you dropped a ball. What will happen? This ball will move along this path, passes through this point, and will reach the same height. Because there is no friction, the ball will reach the same height, and again it will return back. After reaching the same height, it will return back, and the motion is going to continue for the longer time, or you can say for the infinite time, because I have assumed no friction. So what I'm saying, that ball is moving to and fro. To and fro is what? Ball is moving like that. About this point, ball is moving like this. About this point, this motion is called as to and fro motion. Or you can say ball is repeating its motion, but it has a certain boundary. It has some boundary. It cannot go beyond this line. The ball cannot go beyond this line. That means it has certain boundaries which cannot be crossed. So such kind of motion, which is periodic but has some boundaries, is known as oscillatory motion. I think the term is clear. It is periodic motion with some boundaries. I think boundaries term is clear. Now, what is your task? Your task is to identify some other periodic motions, some other oscillatory motions in your life, the motions that you can consider as oscillatory motions. So try to identify and try to comment. I will look at the chat box. What are the motions that you can consider as oscillatory motions? That means they are repeating its motion after a certain time, after a fixed time, and have some boundaries. So the definition is when a body repeats its motion to and fro. To and fro, I think you can understand about a mean position. This is the mean position. Don't worry, I will explain this mean position in more detail. As we move further, I will explain this mean position term in more detail. So this is called oscillatory motion. In short, what you will remember? You will remember this line. Periodic motion plus boundaries. I think clear. Now, for example, the motion of a pendulum. Have you seen the pendulum in your wall clock? There is a pendulum thing, na? It oscillates continuously. So that's a motion. It has certain boundaries. That's a motion of a pendulum is an oscillatory motion. I think clear. So example is clear. I think everything is clear now. So when we talk about repetition of things or a fixed interval after which things are repeating, then there is a necessity of defining a term which is known as time period. So we are going to define time period. I think this is a very simple term. You all know this term from your very, you will say from the class 6th, 7th or whatever. So what is time period? If I say, listen to me, look at me. Time period is the time after which motion is repeated. After which motion is repeated. Or you can say the time to complete one oscillation. The time to complete one oscillation is called time period. The time interval after which the motion is repeated is called time period. Or you can say, or what you can say, the time to complete one oscillation is called time period. It is denoted by what? Capital T. Then what will be the unit of time period? This is again a very fundamental, very basic thing. What will be the unit of time period? Just reply unit of time period, time period. The time to complete, it's a time. It's a time. If it's a time, then its unit is second. Unit is what? Second. Moving further. Very fundamental, very basic thing. Frequency. How many of you know this term? What is frequency? This is a very fundamental term, I will say. What is frequency? Frequency is what? Number of oscillations completed in 1 second. Number of oscillations, like particle is oscillating like that. If a particle is oscillating like that, then number of oscillations completed in 1 second. The number of oscillations per second is known as frequency. It is denoted by what? Small f. Okay. So what will be the unit? What will be the unit? Number of oscillations per second. Per second. Number of oscillation. Number is unitless quantity per second. That means unit is what? Second inverse. And if unit is second inverse, you can say second inverse is also known as hertz. It is also known as hertz, denoted by Hz, hertz. Okay. Now, there is a relation between frequency and time period. I think all of you know the relation, but I will again describe this relation. Let's see. Let's see. Suppose what I'm saying, let's suppose time is mentioned here and number of oscillations are mentioned here. What I am saying, in time t, do you remember what is this time t? Capital T is what? Time period. T is the time in which one oscillation is completed. So you will say in time t, one oscillation is completed. In time t, number of oscillations are what? One. So in 1 second, this is t seconds. In 1 second, how many oscillations will be completed? You will say 1 by t. Is it clear? In t seconds, one oscillation is completed. Then in 1 second, 1 by t oscillations will be completed. And 1 by t oscillations, the definition says number of oscillations completed in 1 second are nothing but frequency. So what we get, frequency is equals to 1 by t. I am again saying number of oscillations, how much? 1 by t in how much time? In 1 second is known as frequency. So frequency is nothing but 1 by t. And from this relation, you can check the unit is second inverse. So this relation, you should remember that frequency is inverse of time period, or f is equals to 1 by time period. Till now, everything is sorted. Now we are going to start the basic thing of our chapter. The name of the chapter is simple harmonic motion. So that's the what we are going to start. Listen to me now. Be focused. This is going to be a new thing for you. So be focused. I think you have written or noted everything till now. Simple harmonic motion. So I don't worry. Don't just confuse harmonic. The meaning of harmonic is nothing but periodic. Simple periodic motion is not like that cute word. So that's why in place of periodic, we are using the term harmonic. So harmonic is nothing but the oscillatory type of motion. Harmonic motion is what? Oscillatory motion. And this is going to be a simple harmonic or simple oscillatory motion. Okay, let's discuss. Any oscillation called as SHM with some conditions. Now I'm going to explain some conditions. Listen to me very, very carefully. Any oscillatory motion will be called as SHM if number one condition, listen to me, if the acceleration of the particle, if the acceleration of the particle is zero at a particular point of the path. Whatever is mentioned there, just look at that after some time. But the thing I am telling you, listen to that very carefully. First thing that I am telling, first thing, acceleration should be zero at any one point of its path. The thing is, if a particle is executing oscillatory motion, then along its path, at any one point, acceleration must be zero. Then this oscillatory motion may be called as simple harmonic motion. First condition, this was the first condition. What is the second condition? At all other points, acceleration shouldn't be zero. At all other points, acceleration shouldn't be zero. At all other points, A is not equals to zero. I think this is clear. 2 points are clear. Third point. What is third point? If at all other points acceleration is not zero, then this acceleration must have some magnitude and must have some direction. Must have some magnitude and must have some direction. So what is the magnitude? This acceleration should be proportional to the displacement. This acceleration should be proportional to the displacement. X is what? Displacement. And displacement from where? From mean position. Next point is fourth point. And the direction of this acceleration should be towards the mean position. And the direction of acceleration towards the mean position. So these are the four conditions for a oscillatory motion to be. Remember with me, along its path, there must be a point where acceleration is zero. There must be a point where acceleration is zero is known as mean position. So now mean position is clear, I think. What is mean position? the position or the point where the acceleration is zero. At all other points, acceleration is not equals to zero. And if acceleration is not zero, then it must have some magnitude and direction. The magnitude should be proportional to displacement. Displacement from where? Mean position. And direction of the acceleration should be towards the mean position. Now I have mentioned all these things in the slide. Look at that. What are the conditions? The acceleration of the particle is always in the direction of a particular point. And this particular point is known as mean position. I think I have explained all these things to you. Again, the acceleration is directly proportional to the displacement from the mean position. Can you identify first point is which point out of these 4 points? The first point mentioned here is which point out of these? Have you got something? 4 points. Note it down. And ultimately, if I conclude all these 4 points, what will I say? That acceleration is conclusion thing is acceleration is directly proportional to what? Displacement. Clear? And the direction is towards the mean position. And if the direction is towards the mean position, then you will say there is a minus sign which indicates that direction is always towards the mean position. That means for a motion to be to be SHM, the condition that is to be followed is acceleration should be proportional to minus of x. Minus of x means negative is indicating towards the fundamental and basic condition. Now, moving further. The example of simple harmonic motion or the SHM is a spring block system that I am going to present here on the screen. Let's suppose, let's suppose this is a spring and this is a block, and the block has some mass m. A spring has some spring constant k. Clear? Now, the spring is now in relaxed position. It is neither elongated nor compressed. This is in natural length. This is the natural length of the spring. Now, what I have done, I have compressed the spring. I have compressed the spring. Now, can you see that if I compress the spring in the work energy power chapter, I have explained to you that whenever the spring is compressed, it exerts a spring force. And if it is compressed, it will try to return back to its original position, and spring force will be in this direction. Is it clear? And if spring force is in this direction, the block will have the acceleration in the positive x direction. Block will have the acceleration in the positive x direction. Can you see that when spring was relaxed at this position, it has zero acceleration. It has zero acceleration because it was at rest. No force was there. It was just relaxed and no acceleration is there. When I compressed it, the acceleration is created in the positive x direction. Now, if I extend it or stretch it, in which direction force will act? In which direction force will act? You will say in the negative x direction, force will act. So acceleration will also be in the negative x direction, negative x axis. So what I'm saying, that every time when you stretch or compress the spring, the acceleration of the block is always towards a certain position, or you can say always towards the mean position. And this is the first condition of SHM. The acceleration is always directed towards mean position or towards a particular point, and that particular point is where acceleration is zero. One thing is clear. Now, what we need to prove here, that acceleration is going to be proportional to x. Acceleration is going to be proportional to x. Let's suppose the displacement is x. Let's suppose the displacement is now. You know that from Hooke's law, now a lot of students may not remember what is Hooke's law. Do you remember what is Hooke's law? That we have studied in work, energy, and power chapter. That spring force is equals to negative of kx. That's what the Hooke's law. Spring force is equals to minus kx. Do you remember this thing? I think. Now, this spring force is acted on the block. So you can write it as, from Newton's second law, F is equals to mass into acceleration. Mass of the block is m. Let's suppose its acceleration is a, is equals to negative of kx. So a is equals to negative of k by m into x. Can you see here that k is the spring constant, which is a constant term? M is the mass, that means k upon m is a complete constant. And k upon m is a constant, so we can assume it as something like that. Let k over m is a constant, and it is denoted by omega square. Generally, it is denoted by omega square. So what will become? A will become minus omega square x. A will become minus omega square x, or you can say A is directly proportional to negative of x. A is directly proportional to negative of x, and this is the most basic and important equation. Whenever we talk about SHM, this equation should be remembered. In class 12th, lot of questions will be done using only this simple relation. A is equals to minus omega square x. And at that time, whether if I am taking the class or whoever is taking the class will ask you this question, even starting from the first chapter of 12, that this is the basic fundamental equation that you have learned in class 11. So try to remember this out, that acceleration is equals to negative of omega square x. What is omega called here? Omega is a constant. And what is its value? You can say omega is equals to root of k by m. You can see this. Omega is equals to root of k by m. Try to write down every term. Omega is equals to root of k by m. One thing. And this omega is known as or called as angular frequency. Omega is known as angular frequency. I think till now every point is clear. We have justified that spring block system moving in a horizontal surface or horizontal direction is an example of SHM. What is the acceleration? Negative of omega square x. moving further. And the next thing that we are going to do is a difficult one, that is the equation of SHM. That is the equation of SHM. For that to learn or to understand, you should know a simple differentiation and simple integration, because we are going to use both of them. Okay, so I hope you are ready for that. Let's start. Let's consider, let from this diagram, I am not redrawing the diagram. I am just assuming that this diagram is in your mind, and I am on the next slide. When I am moving on the next slide, this diagram is in your mind. I hope that. So what I am saying, let at time t equals to 0. Okay, let me draw this to you again. For example, let's suppose this is a spring block system, and this spring block system, let's suppose the spring block system is stressed by some distance x, and displaced by a distance x. Now, what I am trying to do, there are lot of variations, lot of things we can drive it in different manners. But the thing is, for your understanding, for your better understanding, I am driving it for a special case and will generalize it later. Will generalize it later, because if I drive it in the general case, then it will become a very lengthy process for you to understand. Okay, so the special case that I am taking is, I will explain it to you. I am taking it at t equals to 0, particle is at mean position. What I am taking, at t equals to 0, particle is at mean position. This is the special case that I am considering. But in general, this is not the case. In general, it might be possible that when you start seeing the motion, it is at some other position. Like for example, if I stretch this spring out, can you see my hands? For example, this is a spring attached with the wall. If I stretch this spring out, stretch this block out, this block will start moving like that, like that. So when this block is moving like that, this is the SHM motion, simple harmonic motion. And the time when you start seeing the motion, maybe the time when the block is at extreme position, maybe the time when the block is at mean position, and maybe the time when the block is at somewhere between those 2 points. So it might be any situation. So what I am considering here, for the simplicity, at t equals to 0, particle is at the mean position. That's what I am considering. Clear? So I have considered it here, so there is no need to mention, to write it again. I am erasing this lag term because I have explained it to you. Now, for SHM, what we have seen that A is equals to minus omega square x. That's what we have seen already. Now, you can write A as A is the acceleration. So A can be written as dv over dt is equals to minus omega square x. I think it is clear now. Now again, if I say this is x, the term related to x. X is the position. This is velocity and this is time. If you see here, we need to integrate the things. And if I need to integrate the things, then there must be a term related to x or dx. If x is there, there must be a term dx. Okay. There is one thing that might come in your mind, sir. What is the meaning of equation of SHM? What we are going to do? So the meaning of SHM is, or equation of SHM is, relation between position and time. Relation between position and time, or velocity and time, or acceleration and time, is called equation of SHM. In general, most of the times people, whenever you ask someone what is the equation of SHM, they will say that relation between position and time is the equation of SHM. But general thing is that all these relations are equation of SHM. So what is our purpose here is to drive a relation between position and time. For what? For the particle executing SHM motion. So that's why I am trying to introduce the X term here. I think till now everything is clear. Okay. So for that purpose, I need to introduce X. So I am multiplying this term with dx and dividing it with dx. Now again, if most of you know that dx over dt, what is dx over dt? You will say dx over dt is nothing but the velocity. Is it clear now? Let me know that you, whether you know dx over dt is velocity or not. So I will write it again. Dx over dt is v. Dv is already there, is equals to minus omega square x, and this dx is I am transferring here. Now in the next step, I am going to integrate the things. I am going to integrate the things. For integration, I need to put the limits. I need to put the limits. So for example, I am considering when you put the limits of x, initially it was at the mean position. Mean position means 0. And finally, it is something at position x. It is displaced by a position x. I am considering that at the mean position, its velocity is v naught. I am considering this term that at the mean position, its velocity is what? V naught. And at this position, its velocity is v at time t. So velocity is changing from v naught to v. Now the integration is v, integration of v is v square by 2. That means 1 by 2 v square. And if you put the limits, it will become v square minus v naught square is equals to, minus is already there. Omega square is a constant. If you integrate x, it will become x square by 2 and x square. If you put the limits, it will again become x square minus 0. This is what I think I have missed one step here, the value, the step in which we will put limits. So I think you can take 1 second or 5 seconds to realize what's happened here. You can cancel out 2 from here. Is it clear? So what you will get, v square is equals to, this v naught square I am transferring here, v naught square minus omega square x square. I think it is clear now. Let's suppose this is equation number 1. This is not a easy derivation. So be alert and try to listen every point. After reaching this point, I will introduce one more thing. Can you imagine one thing? Just look at me. Again, consider that spring block system in your mind. Like you have stretched the spring and released it. So it will move like that. It will move like that now. Can you see that after reaching a certain distance, it returns back? After reaching a certain distance, it returns back. Why is it returning? Because at this point, its velocity is zero. Because at this point, its velocity is zero. Can you see that? When you throw a ball in the upward direction, after reaching a certain height, it returns back. Why it returns back? Because at the highest point, its velocity becomes zero. In the same way, at the extreme point, the velocity of the particle becomes zero. So I am using that relation. I'm going to use that relation to create a very important relation for you. Look at me. What I am saying. Class is being extended, I think, by a few minutes. So what I'm saying, at the extreme position, do you know the meaning of extreme position? Maximum distance position. What will happen? Extreme position means the x is equals to a. What is a? A is the term amplitude. You have heard that term, I think. What is the meaning of amplitude? The extreme position. X is equals to a and v is equals to zero. I think it is clear. At the extreme position, x is equals to a and v is equals to 0. So I will put these values in equation 1. From equation 1, I am putting these values. So v is equals to 0, v naught square minus omega square a square. X is equals to a, v is equals to 0. So from here, what you get? You will get v naught square is equals to omega square and a square. Is it clear? So V naught, you can say that V naught is a constant term. V naught is a constant term which has a value omega square a square, or V naught is equals to a omega. You will see that relation. Now again, I am saying, put this value of V naught square in equation 1. Again, from equation 1, I am putting this value, so it will become V square is equals to V naught square is what? Omega square a square minus omega square x square. V will become, you can take omega square as common. So V will become omega root of a square minus x square. This is the golden relation. This is the golden relation. You need to put it in a golden box, because in most of the numericals, this relation is going to be used. This is what this relation tells us. This relation tells us the velocity of the particle at any position x. You are not getting what I'm saying. This equation tells us what is the velocity of the particle at any position x. In the numerical section, you will see a lot of questions are coming from this equation only. So try to put this equation in a golden box, make it a punchline, make it a highlight of the session, and write it down. Now I am moving further. This is not the relation that we wanted, but this is an important relation. Now moving further. Moving further means what we have achieved till now. We have achieved V is equals to omega root of a square minus x square. We need to find the relation between x and t. Can you write velocity as dx over dt? Yes, you can write velocity as dx over dt is equals to omega root of a square minus x square. This is the derivation which is going to be asked in your exams. Lot of time it is being asked. So dx over dt is equals to omega root a square minus x square. Again, if I say transfer the things, x should be related to x. So I am transferring the things like dx over root of a square minus x square is equals to omega dt. Now integrate the things. Integrate the things. Now, if you are integrating, you need to put the limits. I am putting the limits. Time that I have seen from 0 to t. At 0, particle was at mean position, that means 0. And at t time, it is at a distance x from the mean position. You need to put the limit. You need to know how we are putting the limits. If it was initially not at 0, there must be a limit kind of x naught thing here. But we have taken a simple case. What is the integration of dx over root a square minus x square? Anyone knows that? If anyone knows, he can tell me. Otherwise, I am telling you it is sine inverse x by a. Limit is what? 0 to x is equals to omega is a constant. Dt is what? T. Limit is again 0 to t. So after putting the limits, what you will get? After putting the, you will get sine inverse x by a is equals to omega t. If you remove this sine inverse from here, you will get x by a is equals to sine omega t, or x is equals to a sine omega t. This is a special case when particle was at mean position at t equals to 0. If it was not so, ऐसा अगर नहीं होता, उस केस में the general equation what we will get, the general form will be x is equals to a sine omega t plus phi. A constant will be added here if it was not at mean position initially. This phi is known as, only this phi is known as phase constant. I will explain all these terms in the next class. What I'm saying, what is this phi known as? This phi is known as phase constant. And can you tell me what is this A known as? What you have seen, A is denoted by the amplitude. A is what? Amplitude. What is this omega known as? Omega, don't read it W, it is omega. What is this omega known as? Angular frequency. Don't ask me about T. T is what? Time. Don't ask me about X. X is what? Position of the particle. X is what? Position of the particle from where? From the mean position. I think clear? Okay. So what you need to remember after the session, you need to remember what is periodic motion, what is oscillatory motion, what is SHM. These three things. If you add some boundaries in periodic motion, then it will become oscillatory motion. If you add certain conditions related to acceleration in oscillatory motion, then it will become SHM. What are the conditions for SHM? You need to remember. After that, what is the equation of SHM? You need to remember. And the general form of equation of SHM is that is to be again put it in the golden box. And on behalf of that, we are going to end the session. And in the next session, we will discuss. Next session is also from 3 p.m. Try to note the time, is also going to be started from 3 p.m. And we will see you. Till then, bye bye. Enjoy. I'm going to end the session.